Hello everyone, welcome to our channel Masters in Chemistry. Today I would like to discuss the topic Stereo-Isomers. In stereochemistry, I would like to discuss the few topics: optical isomers, optical active isomers, optical inactive isomers, enantiomers and diastereomers. Now we'll see the topic step by step. Friends, you see here. Now let me ask a question. What is known to be an optical active compound? And this optical active compound, when we are discussing, the optical active compound must contain chiral. Chiral compounds are optical isomers. Chiral compounds are known to be that optical active compounds. Now last question, right? What is known to be chiral? The Greek word chir indicating that hand-like molecule. Just we would like to check our left and the right hand. The left hand containing 5 fingers and the right hand containing the 5 fingers. Now these 5 fingers were different, right? Like this. And the left and the right hand both having the mirror images, right? Left hand mirror image is right hand. And the right hand containing mirror image is left hand. Now, when you're taking an isomer and that isomer is known to be an optical active, it must containing the following conditions. I will tell you. The first condition, it should have all attached atom or the group, they should be different based on its valency. Now, when I'm discussing about carbon compounds and this carbon valency equals to 4. Okay. Now, we will have an example here. Just we will see in detail what is known to be a chiral molecule. In this example, I'm taking chiral molecule. Now I'm taking an example. Here I'm taking a carbon containing compound, and this carbon containing is a methyl, Cl, bromine, and hydrogen. Now I'm taking it is known to be 1, and it is known to be 2, and bromine is known to be 3, and hydrogen is known to be 4. Then what happened? 1 not equals to 2 not equals to 3 not equals to 4. So I'm saying this carbon is going to be chiral. What is a chiral carbon? The chiral carbon is nothing but the carbon containing atoms or group, and there should be different. I'm repeating. The different atoms or groups attached to carbon, and that carbon is known to be chiral carbon. Okay. Let me have a clear explanation here. What is the difference between a chiral and a chiral? You see here. What is known to be a chiral? The word achiral indicating that it may containing similar atoms or group. Hydrogen is here and hydrogen is there. Hydrogen will be the same, followed by methyl and bromine. It is not a chiral. It is not a chiral. It is known to be achiral. What is the difference between chiral and achiral? Chiral molecules which containing atoms or group, hydrogen, methyl, Cl, Br. 4 different groups are attached to carbon, and this carbon is known to be chiral. If this possibility is not takes place, then they are known to be achiral or symmetric molecules or achiral molecule. Asymmetric molecules are chiral molecules. Now we'll see the continuation very clear. Now when we are taking chiral molecule, this chiral molecule must containing mirror image. Okay, the first condition is chiral molecules always exhibiting mirror image. The best example I'm taking left hand is chiral. Why? Because left hand containing how many fingers are there? 1, 2, 3, 4, and 5. Like this. And I'm taking the right hand. And this right hand is also containing 5 fingers. That like this, when we are taking as a carbon compound valence equals to 4, and 4 should be different. The valence equals to 4 and 4 should be different. Okay, see this. Now, any of chiral compound, when we are discussing, the chiral compound it should contain mirror image. And those mirror images are non-superimposable. Cannot be superimposable. Let me ask you a question, right? What is known to be non-superimposable? You see here, it is the left hand and it is known to be right hand. The left and the right hands, they are not superimposable. When we are placing the left hand on the right hand, which is non-superimposable. Okay. Chiral molecule, the first condition, it must contain a chiral center. The second condition, it should have mirror images. The third condition, the two isomers are non-superimposable. I'm repeating. The two isomers are known to be that non-superimposable. Now let me have a conclusion here. A molecule is considered chiral if there exists another molecule that is of an identical composition but which is arranged in a non-superimposable, I'm repeating, which is arranged in a non-superimposable mirror image, and also presence of asymmetric carbon. And this point is very, very important. It should contain non-superimposable mirror image, and the carbon should be asymmetric. The carbon should be chiral. Now the property is known to be that chirality. Now we will see the next slide. In the chiral compounds are classified into two main classifications. The first classification is enantiomer and the second classification diastereomer. I will tell you what is the difference between enantiomer and diastereomer. Okay. The optical active pairs, which is non-superimposable mirror images, and both are known to be optically active, they are known to be enantiomer. Simple example, just now we have taken optical active isomer, which is having the mirror image, and both are known to be optically active and they are non-superimposable. Left hand have the mirror image, is right hand. Okay, like that you are taking the chiral compound A, and this chiral compound A containing mirror image is known to be chiral compound B. When we are taking a chiral molecule, and this chiral molecule containing a mirror image, and both of the mirror images are non-superimposable. I'm repeating. Both of the mirror images are non-superimposable and both are known to be optically active. And the optical active pair, they are known to be the enantiomer. We will see the definition. Enantiomers are chiral molecule that are mirror images of one and another. First point. Enantiomers are mirror images to one and another. Furthermore, the molecules are non-superimposable. Number two, non-superimposable. This means that the molecule cannot be placed at top of another and give the same molecule. Chiral molecules with one or more stereocenters. I'm repeating, what is stereocenter? Stereocenter may be chiral centers, right? That simple definition. What is an enantiomer? Enantiomer, the first condition but containing chiral, stereogenic center. Number two, it should contain mirror image. Number three, and both mirror images are non-superimposable. And the fourth condition, they are optically active. Can I repeat again? Number one, chiral center. Number two, non-superimposable mirror images. Number three, optically active pair. Now we will see some of the examples of enantiomers here. Now see friends. And here I am taking an example for enantiomer. Now it is known to be carbon. And this carbon containing chlorine, hydrogen, methyl and bromine. Okay. Now see this. It is containing the mirror image. Now this hydrogen should be on the rear side. Same. That hydrogen should be here in the other side. I'm saying hydrogen on the left hand side and here the hydrogen on the right hand side. Hydrogen on the right hand side. Then chlorine, bromine, chlorine, bromine. Now it is known to be 1 and it is known to be 2. What is the first condition for enantiomer? The first condition for enantiomer, it must contain chiral, Cl, hydrogen, bromine, methyl. 1, 2, 3, 4. A not equals to B, B not equals to C, C not equals to D. So this carbon is known to be chiral carbon. Now I will take the mirror image of 2 carbon, Cl, hydrogen, bromine, methyl. A not equals to B, B not equals to C, and C not equals to D. It is also known to be chiral. A is known to be chiral and B is known to be chiral. A is optically active, B is optically active, and both are known to be non-superimposable mirror images. I'm repeating. A and the B, they are known to be non-superimposable mirror images. How we can say hydrogen here is the left hand side, hydrogen here on the right hand side, and methyl here is the left hand side, and methyl is placed on the right hand side. Methyl on the left hand side, and the methyl group on the right hand side. hydrogen on the right hand side, hydrogen on the left hand side. They are known to be non-superimposable mirror images. It is known to be an enantiomeric pair. Can we take another example here? You see this. Now taking another example, you see this. Number 1 carboxylic acid, number 2 hydrogen, number 3 OH, number 4 CH3, COOH, HOH, CH3. A not equals to B not equals to C, and C not equals to D. So this carbon, what we are saying as a chiral carbon, asymmetric carbon, and it containing mirror image, hydrogen on the right hand side, and here the hydrogen on the left hand side. Now this carbon is a symmetric carbon, COOH 1, hydrogen 2, OH 3, and CH3 is 4. Okay, A not equals to, B not equals to, C not equals to D. A not equals to, B not equals to, C not equals to D. Now both isomers, they are known to be chiral molecule which containing stereogenic centers. They are nothing but non-superimposable mirror images, just like left and right hand. The continuation we will see another example. Now here I am taking another example like 2-bromobutane. I am taking here 2-bromobutane. 2-bromobutane can be written like this. It containing, this is a carbon, and it is also carbon which containing CH3 methyl. Carbon, hydrogen, carbon with hydrogen, and carbon with the hydrogen. You see here. Carbon, CH3, hydrogen, Br, and ethyl is here. Now, I'm taking the 2-bromobutane like this, then this first functional group 1, it is 2, and it is 3, and it is 4. 1, 2, 3, and 4. Ethyl on the left hand side. Which side here? Left hand side. Mirror image. Ethyl on the right hand side, which containing asymmetric center. And here is also it containing asymmetric centers. So 1, it's 2, and 3, and 4. Okay, simple. A not equals to B not equals to C, and C not equals to D. Now 4 different groups attached at the carbon, chiral carbon. The 4 different groups attached at the carbon, chiral carbon. Asymmetric carbon, asymmetric carbon. Optical active isomer, optical active isomer. Then A isomer, and it is known to be the B isomer. A isomer having the mirror image is B. A containing mirror image is B, and the B containing mirror image is known to be A. Friends, now we have seen the next category of stereoisomers. The second category of stereoisomers, I am discussing diastereomer. I am repeating. What is known to be diastereomer? When we are discussing diastereomer, and these diastereomers are isomers which containing 2 isomers, 1 and 2. One is optically active and the other one is optically inactive. I am repeating. One is optically active and the other one is optically inactive. The next condition, which is having non-mirror images, A and B are non-mirror images and non-superimposable, non-identical structures. What is known to be diastereomer? Simple. Diastereomers are non-mirror images. Diastereomers are non-superimposable and non-identical stereoisomers. I'm repeating. Non-mirror images, non-identical stereoisomers, non-superimposable. Now we can have an example for diastereomer. Now we will have an example here. The best example for diastereomer. This is an isomer, right? Okay, and here I'm taking another isomer here, and I'm taking a third isomer here. Let me take it is 1, it is 2, and it is going to be 3. Now, this carbon is chiral, and this carbon is chiral. This carbon is known to be chiral, and this carbon is known to be chiral. Simple. This carbon is known to be chiral, and this carbon is known to be that chiral. There, simple. Now see here, OH on the right hand side, okay, and here the OH on the right hand side. Bromine on the right hand side, and here the bromine on the left hand side. Now when we are taking the 2 isomers, right? Now let me have a comparison, which is diastereomer and which is enantiomer. You see this. Now here. Now let me ask you a question. you should identify which is enantiomer, which is diastereomer. You see this. These two isomers, they are known to be diastereomers. These two isomers known to be diastereomers. Now I'm taking these two isomers, and these two isomers are non-mirror images. OH on the right hand side, okay, OH on the left hand side. Bromine on the left hand side, but here bromine on the left hand side. They are known to be diastereomers. Okay. Now, what is diastereomer? Diastereomers are non-mirror images. The first condition, non-mirror images. What is the second condition? Non-superimposable. Non-mirror images, non-superimposable. Can you identify what is enantiomer pair? We can identify the enantiomeric pair. Now this pair is known to be enantiomer. How we can identify? It is known to be chiral center. It is known to be that chiral center, and this carbon is known to be chiral, and this carbon is also known to be chiral. OH on the right hand side, OH on the left hand side. Bromine in the right hand side and the bromine in the left hand side. Now, and both are known to be mirror images and non-superimposable, which containing asymmetric centers. It containing asymmetric centers, both isomers containing asymmetric centers, both are known to be mirror images and both are known to be non-superimposable. So, in the structure 1 and so this is structure 1, it is 2 and it is 3, 1 and 3. 1 and 3, what we are saying is enantiomer. Enantiomers are 1 and 3. Then what is diastereomer? Diastereomers are 2 and 3. 2 and 3 is known to be diastereomer. These two pairs we can take it as diastereomers. They are known to be diastereomers. Now these two pairs we're taking as enantiomer. They are known to be enantiomer. Okay. Now we'll see another example. The next one I'm saying as a meso compound. What is known to be a meso compound? A meso compound is optically inactive. It must containing internal plane of symmetry. Even though it containing chiral center, it is not optically active. A meso compound is optically active because of only one reason, which containing internal plane of symmetry. Okay, it may containing the two stereogenic centers. It may containing the two stereogenic centers. Because of internal plane of symmetry, it is known to be optically inactive. Let me clarify. Now see this. I will explain what is known to be a meso compound. Okay. Now we can have this example. This is 3 and it is known to be 4. Both are mirror images. I can take it as it is chiral carbon and it is chiral carbon. And here I am taking it is chiral carbon and it is also known to be chiral carbon. 1, 2, 3. 1, 2, 3. Okay. Now see, hydrogen on the right hand side, hydrogen on the left hand side, hydrogen on the right hand side, hydrogen on the left hand side. Now these isomers, these two isomers are mirror images. Okay, mirror images. It containing stereogenic centers and they are non-superimposable, but they are not enantiomers. They are not known to be that enantiomers. They are known to be a meso compound. Why I would like to say meso compound is this compound containing internal plane of symmetry. I am repeating. This molecule containing internal plane of symmetry. Cl, Cl, hydrogen, hydrogen, CH3, CH3. Hydrogen, hydrogen, Cl, Cl, CH3, CH3. Any of isomer, any of stereoisomer, if it containing internal plane of symmetry, when we are cut the molecule into two equal halves, if it containing a symmetric center, I am repeating, if it containing symmetric center, it is optically inactive. So, I'm saying these two isomers, I'm repeating friends, I'm saying these two isomers are optically inactive. They're optically inactive. Why? Because it's containing internal plane of symmetry. It is optically inactive. Why? Because it's containing internal plane of symmetry. Okay. Meso compound. What is the difference between meso and enantiomer? Enantiomeric pair is optically active. Meso pair is optically inactive. Enantiomers, which do not containing any plane of symmetry. Meso compound containing internal plane of symmetry. Now we can go through the continuation. Now we can have another example for meso compound. You see this. It is chiral. It is known to be chiral, and this carbon is known to be chiral. OH on the right hand side, OH on the right hand side. Now here. Now this part is known to be chiral, and it is known to be chiral. Simple. And this carbon is known to be chiral, and this carbon is known to be chiral. You see here, OH on the right hand side, OH on the right hand side. Here, OH on the left hand side and OH on the left hand side. Then, non-superimposable, stereogenic center, mirror images. But it is not enantiomer. Why? Because it containing internal plane of symmetry. You see this. It containing internal plane of symmetry. When I cut the molecule at the middle place, right, then what happened? It converted into two equal halves. When we are cut the molecule at the center, it converts into two equal halves. OH, OH, hydrogen, hydrogen, CH3, CH3. Internal plane of symmetry. OH, OH, hydrogen, hydrogen, CH3, CH3. Any of isomer which containing internal plane of symmetry, it is known to be optically inactive. It is known to be a meso compound. Meso compound is optically inactive. Right. Now let me ask you a question, right? How we can write optical isomers of different molecules? Now, I will show you the first example, lactic acid. Here I am taking the first example, lactic acid. What is known to be lactic acid? I am writing like this. Lactic acid. The structure of the molecule is like this. Lactic acid which containing one carbon, CH3, OH, COOH, hydrogen. Is it chiral or achiral? It is chiral, which containing a symmetric center. CH3, OH, COOH, hydrogen. CH3 not equals to OH, OH not equals to COOH, COOH not equals to hydrogen. The carbon containing the four different groups. So it is going to be chiral center. It is optically active. When we are finding number of optical isomers, there is a formula. The formula I am saying as 2 power n. Okay, 2 power n is equals to 2 into n is equals to number of chiral centers, and here the number of chiral center is equals to 1. Number of chiral center equals to 1. That is 2 power 1 is equals to 2. Okay, next one. Now we are discussing about the two optical isomers. Simple. OH on the right hand side and its mirror image OH on the left hand side. Hydrogen on the left hand side and here the hydrogen on the right hand side. Okay. Now it is known to be D plus lactic acid and it is known to be L minus lactic acid. How many chiral centers are there? One chiral center. How many optical isomers are possible? The number of optical isomers are identified using the formula 2 power n. 2 power 1. 2 power 1 is equals to 2. Number of optical isomers equals to 2. First one should be D plus lactic acid. Second one should be L minus lactic acid. Dextrolactic acid, levolactic acid. Plus lactic acid, minus lactic acid. Okay. Now, the two pairs, what we are saying as enantiomeric pair. What is enantiomeric pair? The two isomers which is having non-superimposable mirror images. The two isomers having non-superimposable mirror images, which is known to be enantiomers. Enantiomeric pair is optically active. Enantiomer pair is known to be optically active. Next. The next one I'm saying about tartaric acid. What is the difference between tartaric acid and lactic acid? Tartaric acid having two chiral centers. The chiral center 1, chiral center 2. Chiral center 1, chiral center 2. Okay then. Number of optical isomers can we calculate? 2 power n is equals to 2. 2 power 2 is equals to 4. Now 2 power n is equals to 2 square is equals to 4. The 4 optical isomers when you are calculating A, B, C, D. Now see here. OH on the right hand side and here OH on the left hand side. OH on the left hand side. OH on the right hand side. Okay. Now, when we are discussing A and the B, and A and the B both are known to be mirror images. A and the B are mirror images. Next one here. OH on the right hand side, OH on the right hand side, OH on the left hand side, OH on the left hand side. And these two isomers are mirror images. And these two isomers known to be that mirror images. I'm repeating. A and the B are known to be mirror image. And the C and the D is known to be mirror images. Now, what is A and B? A and B known to be that enantiomer, which is non-superimposable mirror images. I'm repeating. A and B are known to be enantiomer. I'm taking this is A, this is B. Tartaric acid A, tartaric acid B. It is known to be dextrotartaric acid and it is known to be levotartaric acid. Now, when we are taking both are known to be non-superimposable mirror images. They are known to be that non-superimposable mirror images. But when we are taking C and the D, even though both are known to be that mirror images, both are non-superimposable, but they are not optically active. Why? Because it's containing internal plane of symmetry. Because it's containing internal plane of symmetry. Okay. Because of internal plane of symmetry, it is optically active. So C and the D, what we're saying is meso. Meso is an optically inactive pair. I'm repeating. Then, what is meant by enantiomer and what is known to be diastereomer? We will see here. A and the B are known to be that enantiomer. B and the C, diastereomer. B and the D, diastereomer. A and the C, diastereomer. A and the D, diastereomer. C and the D, meso. I'm repeating. A and the B, enantiomer. A to C, diastereomer. A to D, diastereomer. B to C, diastereomer. B to D, diastereomer. What is diastereomers? Diastereomers are non-superimposable, non-mirror images. B and the C, B and the D, A and the C, and A and the D, they are known to be the diastereomers. Okay? Friends, today we have discussed what is meant to be stereocenters, what is meant by stereoisomers. Just I would like to remind, just like my hand containing the 5 fingers, and these 5 fingers were different. Just like carbon, the carbon valence equals to 4, and the 4 valencies are satisfied by the 4 different groups, then it is known to be chiral molecule. Then it is known to be the chiral compound. Chiral compounds are the 2 main classification. The first classification is enantiomer, the second classification diastereomer. There is a third classification which containing internal plane of symmetry is known to be mesocompound. I will repeat again. Enantiomers are non-superimposable, non-mirror images, optical active isomers. Diastereomers are non-superimposable, non-mirror images. Okay. Enantiomers are non-superimposable mirror images. Diastereomers are non-superimposable non-mirror images. And mesocompounds are non-superimposable mirror images, but they are optically active because it's containing an internal plane of symmetry. The 3 main classifications we are discussing in stereochemistry is, number 1 is known to be enantiomer, number 2 is known to be diastereomer, number 3 is known to be mesocompound. Okay. Now, what is the difference between optical active mixtures? The equal form of D and the L, the equal form of enantiomeric mixture is known to be racemic mixture. The preparation of racemic mixture is known to be racemization. I'm repeating. The equal form of D and L, the equal form of plus and minus, the equal form of enantiomeric, D lactic acid, L lactic acid. It is known to be racemic mixture. Okay. Now, when we are adding equal amount of 2 optical isomers, results in the formation of optical inactive mixture. Okay. Positive rotation nullifies with the negative rotation. It is known to be the racemic mixture. The process of preparation of racemic mixture is known to be racemization. The continuation of stereochemistry topics, stereoisomers, we will discuss in the next coming class. Thank you for watching. Thank you. Thank you.